Okay, welcome to part 3 of my review for the Astro 2 quiz. This is the last part of this review. I'm going to go over Supernova Type 1 and General Novae and how we create heavier elements. So we learned before in class about white dwarfs, and we learned that white dwarfs have a mass limit. Right, this mass limit is 1.4 solar masses. White dwarf mass limit. So normally that's fine. White dwarfs get created and they're 1.4 solar masses or less, and then they just cool off over time. But in certain cases, that mass limit comes into play. So when you have two stars that are orbiting each other, right, you've got a star and a star. They are both pulling on each other with gravity, right? This guy is pulling on this guy. This one is pulling on this one. And everything in between. This one has more mass, so he has a stronger gravitational pull. This guy has less mass, so he has a smaller gravitational pull. But gravitational pull gets smaller as you get farther away from the mass. So at some distance between the two, their gravitational pull is going to be equal, right? So this guy has more gravity, but it gets smaller as it falls away. So as you get closer to this guy, his gravity is increasing, and somewhere between them, the gravity is going to be equal. So things on this side of the line are going to get pulled more towards this small one. Things on this side of the line are going to get pulled towards this large one. And this line is going to be closer to the less massive star. So eventually what can happen is this one expands as it goes into its red giant phase, and its outer layers get out here past this line. And these outer layers are going to stop being pulled towards this star, and they're going to start being pulled towards this star. So they're going to go onto this star. If this star is a white dwarf, and it's now got mass adding onto it, it's can increase over this mass limit. And this is the limit that electron degeneracy pressure can hold this star up, right? So you add mass on to this star. One thing that can happen before you reach this mass limit is you're adding mass onto this star, and it acts like sort of an insulating blanket, and you heat up. And if you heat up enough, you can get fusion happening. And you get this burst of fusion, and all of a sudden, this star, this used to be a white dwarf, which doesn't create its own light, it just has the light from its heat that's cooling off, all of a sudden it's making light. And it gets so much brighter, like right away. And so that, they call this a nova, right? That nova is new because these were stars that were too faint to see before. They were just these faint white dwarfs. And all of a sudden, they've got fusion and they're creating their light. So if you look at that spot in the sky, all of a sudden, you see a new star. There was something there before, but it got so much brighter that now you can actually see it. Hi, buddy. So that's just a regular nova. But if you add more and more and more and more mass on till you get over this 1.4 solar mass limit, then something else happens. So these white dwarfs are held up by something called electron degeneracy pressure, right? We talked about this in the last section. And if you get over this 1.4 solar mass limit, electron degeneracy pressure can't hold it up anymore, and it starts to collapse. And when it starts to collapse, it gets really dense, and the pressure goes up, and the temperature goes up. And when the temperature goes up, this sets off a ton of nuclear fusion and nuclear reactions. And so we talked about previously how in equilibrium you can only fuse up to iron. That's like the heaviest thing that you can make with these equilibrium nuclear reactions. But in this runaway thermonuclear reaction that's happening, you can actually create a couple more things in what are called non-equilibrium fusion reactions. And what you can make is cobalt and nickel, and those are just a little bit up from iron on the periodic table. So you have this huge explosion, this runaway nuclear bomb that's gone off in the center of your star, and it creates a bunch of fusion, including cobalt and nickel, right? And then that cobalt and nickel is radioactive. So when we look at what is called a light curve from this explosion, it looks like this. Right, you have your big explosion where the amount, so this is intensity, and this is time. The amount of light increases a bunch. Right, so here's your explosion. And then, the explosion stops, so you would think that it would just fall back off. But it doesn't. Instead, it looks like this. So where does all this extra light come from? There's still light being generated. So this extra light comes from that nickel and cobalt that were created in these non-equilibrium reactions. They are radioactive, and so they decay down to other elements. Nickel decays to cobalt, which decays down to iron, which is stable. And every time they decay, they put off some energy. They put off some light. So when we measure this energy, this light curve, we get the big bump from the explosion. And then as this nickel and cobalt decay, they're still putting off energy. But as they decay, there's less and less of them. So there's less and less that are able to decay. So there's less and less energy over time until they're all done decaying and you just have iron left. Right? So this process, this white dwarf getting mass accreting onto it until it collapses and then explodes in a runaway thermonuclear reaction, it's called a supernova type 1. Right? Type 2 supernova are what we did in the previous section or previous part of this class. That's the core collapse, where you have a massive star, the core collapses down, you have a big explosion of the outer layers, and you're left with a neutron star or black hole, right? This type 1, this is a white dwarf supernova. So you have mass accreting onto the white dwarf, it gets over this 1.4 solar mass limit, collapses down, heats up, causes these thermonuclear reactions, which create a bunch of fusion, including non-equilibrium reactions that make nickel and cobalt. That nickel and cobalt then decay, and that decay creates this extra tail of energy. So, looking at the homework, problem 1 says, which of the following are part of the scenario for supernova 1? So mass transfer from a close companion onto a white dwarf. That is true, right? That's where it gets the mass from. The collapse of a white dwarf whose mass exceeds 1.4 solar masses. That's true, right? If it gets over this limit, it's going to collapse. The iron core of a massive star reaches the Chandrasekhar limit. So that's for supernova type 2, not for type 1. So that's false for this. core collapse, neutronization, neutrino production, and shock waves. That is also for type 2. That's not for type 1. That doesn't happen for this. And then question 2 says, in a supernova 1 outburst, the initial burst of light is due to the energy released in fusion reactions. What keeps the supernova 1 glowing after the first 15 days? So is it neutrino heating? No. Photodisintegration of iron nuclei? No. Radioactive decay of hydrogen and helium? It is radioactive decay, but it's not hydrogen and helium. Those don't decay easy. Otherwise, hydrogen and helium are what most of the universe is made of. So if those were decaying all the time, then the universe wouldn't be made of them. And hydrogen can't really decay down to anything else. It's just a proton. And then radioactive decay of nickel and cobalt formed during the explosion. That is the answer. This nickel and cobalt are made during the explosion in these non-equilibrium reactions. They decay. That decay gives off light, and it gives you this long tail after the initial burst of light from the explosion. So that is supernova type 1. And then the other thing that I want to talk about is how do we get heavier elements? So we learned in class, that we don't really make anything other than up past iron in fusion. And sometimes in these non-equilibrium, you can get nickel and cobalt. But stuff past that isn't going to be made by fusion. So to understand why these aren't going to be made, we need to look at this chart. And down here is number of nucleons in the nucleus, or number of particles. So this is number of protons plus the number of neutrons. And then over here, this is mass per particle in the nucleus. And it makes something that looks kind of like this. Down here at the bottom, this is iron. We've got cobalt and nickel all right here kind of at the bottom. Up here, with just one proton, you've got hydrogen. And then helium has 2 protons and 2 neutrons. So that's 4. So we've got, at 4, here is helium. And then going down, you have carbon and oxygen and all sorts of stuff till you get down there. And over on this side, you have stuff that's heavier than iron. We've got like lead here, all the way over here at the end is uranium. Well, not quite at the end, there's heavier stuff, but uranium's down there. So on this chart, if you are fusing or going from something to that's higher up to lower down, you're going to get energy out. So if I go from hydrogen to helium, I'm going to get energy out. If you go up on this graph, you have to take energy to move up. So if I go from helium to hydrogen, that will take energy. That will use up energy to do that transition. But hydrogen down to helium will give off energy. So hydrogen to helium moving down gives off energy. Helium to hydrogen moving up takes energy. So that means that hydrogen to helium, that fusion will happen. Hydrogen will fuse down to helium and create energy. Helium to carbon creates energy. Carbon to oxygen creates energy, and so on. Over here, if I want to go from uranium to lead to go down, I can do that. That's going to create energy. But that's not fusion. If I want to go from lead to uranium, with fusion, so fusion goes this way. Right? If you are fusing, you're adding nucleons. So if I want to use fusion to turn lead into uranium, that's actually going to take energy. I'm going to have to use a source of energy to make that happen. So it's not going to naturally happen, right? Things only naturally happen if they're going to create energy. So down here at the bottom is this iron, right? So iron can't go down. There's nowhere down for iron to go. And that's why iron doesn't fuse, because there's nowhere down for it to create energy when it makes something. So for these guys, in order to make energy, they need to go this way. And this is the fission way. So if I'm starting from something down here, I know how to make these. We start off with hydrogen. That's what's created first in the universe. And then we make everything on this side through fusion. How do I make these if fusion's not going to happen for them? Right? If I need energy to make fusion happen, how do they happen in the first place? Right? So fusion, you have your nucleus of an atom, and then another nucleus, or just a proton, that's also positively charged, has to get stuck together. But because they're both positively charged, they're repelling each other. So it has to be moving fast enough to get close enough for them to stick together. And they're only going to stick together in the first place if they're going down on this chart. But a lot of times they can't even get close. Like a proton can't just get in. You can't just stick an extra proton in this nucleus. It's not going to be able to get close enough. It's being repelled by the electric force, because positive and positive are going to repel each other. So a proton can't get in to this nucleus. But a neutron, which has no charge, doesn't have to deal with that electric force. So if you have a nucleus of something and it has a bunch of protons and a neutron, protons and neutrons in this nucleus, another neutron that has no charge can come in here and join up and add another neutron in here. And there's not going to be anything pushing it away. So then once this neutron's inside, he says, well, I'm a neutron, but a neutron is basically a proton and an electron squeezed up so close together that their charges cancel out, right? A proton is a positive charge, an electron is a negative charge. So if you stick them right up next to each other and squeeze them together, then their total charge is 0. So this guy says, I'm a neutron, but really all a neutron is just a proton and an electron squeezed up together. So once I'm inside this atom, I'm going to split up into my proton side and my electron side. And I'm going to send my electron out of this nucleus and keep the proton inside. So this neutron turns into a proton and sends this electron out. Well, negative electron. And now all of a sudden this nucleus has another proton, and now it's a new element. So this process is called neutron capture. And then this process here, where the neutron turns into a proton and an electron, this is called beta decay. Right? And this really only happens when you have extra neutrons floating around. And, you don't often have that except in special cases, such as, when in a supernova type 2, when a star is collapsing and everything's being, it's forming that neutron star in the core center. So all of a sudden you have a ton of neutrons and you're able to have them hang around and go into elements. So this happens at 2 kind of time scales. You can add a neutron, maybe at 1 or 2 neutrons, and then they do their beta decay, and it jumps up 1 or 2 spots on the periodic table. And then it adds another neutron, that beta decays, it jumps up another spot, right? This is called the S process. S process is slow addition of neutrons, right? Or if you have a ton of neutrons hanging around, you can add a bunch of them in at once. You can add up to like 100 neutrons into this nucleus all at once. And then they all beta decay, and you jump up a bunch of spots on the periodic table. So this is the R process. R is for rapid addition of neutrons. S process, slow, you add 1 or 2, they decay, jump up 1 or 2 spots, add another one, it decays, you jump up another spot. R process is rapid, you add a bunch of neutrons, they all decay, you jump up a bunch of spots. And that's how we get these heavy elements. And then sometimes these heavy elements, they will have fusion or fission. If they are radioactive, they will go back down. But that's not how most of these are made. They're made through this process. So looking at the homework, question 3 says, which of the following are true and which are false regarding the information regarding the formation of elements with atomic number larger than iron? So the first one says most are made by the addition of neutrons to existing nuclei. That is true. That's this neutron capture process. Most are made by the fusing of light elements to iron. That's false. Iron does not want anything fused to it. It would take energy to fuse something to iron. Most are made by the S process and the R process. That is true. That is the 2 types of this neutron capture. And most are made by fission reactions involving uranium and other rare earth elements. That is false. Some are made, but not most of them. Just a couple of them are made that way. Okay, so I think that is all of the homework problems and everything that needs to be covered for this class. I hope that these videos have been helpful to you guys. Please email me if you have any questions. If I have some time, I'll do a couple like math problem homework examples that I can post as well, but these should have covered all of the homework problems and everything that you need to know for the quiz. And good luck.